The word antibody was coined by Paul Ehrlich before anybody even knew about proteins and DNA. So it was a concept. A body is something that exists. If there's a foreign body like a virus or bacteria, Ehrlich said there must be some way that the body produces an antibody that gets rid of that. A silver bullet, he called it. So he was right. I just didn't know what it was. And by 1975, which I'll pick up, is a guy named Cesar Milstein in Cambridge managed to do something important that's shown on this slide. And this is a method that's still used. Milstein showed is if you inject a mouse or an animal with an antigen, it could be COVID, it could be anything that you want to bind and inhibit, it'll produce these special cells. Each cell produces a protein that's an antibody. And I said it, what's remarkable is our body has a fixed set of maybe 20 to 30,000 proteins that it tries like crazy not to change. No mutations could be cancer. And at the same time, it has a set of billions of antibodies that any single one can arise within a week. So complete opposites. And the antibody cells mutate like crazy, not like normal cells. They produce a protein that's an antibody. And if one of those antibodies does something useful, like neutralizes a virus, the body has ways to make large quantities of those. What Milstein did is he moved that into what's called an in vitro cell-based system. So he could take the mouse cells, make them immortal so they grow forever, and suddenly he had a monoclonal antibody. So one antibody from the mouse is now produced by a cell that you can keep for hundreds of years, and it always produces the one antibody of interest. So this was great because suddenly you could purify, study, and use single antibody proteins. So that was by 1975. But it's still natural antibodies. It has to be first produced by a mouse before you can start. And you'll notice you don't know anything about this antibody except that it neutralizes a virus. We don't have its sequence or structure. So from 75 on, the goal was, can we actually figure out the exact structure of every antibody? And crucially, can we start making our own antibodies? We don't have to bother poor mice. We can do it all in a test tube, so eliminating this part. My group's been instrumental in that. Many other groups, it's been a 50-year team effort. I only got involved in the late 90s, so I've been at it 25 years. And amazingly enough, what I'm showing here is not a cartoon. This is a representation of the molecular structure of an antibody. So you actually know where every single atom in this thing is. This is more detailed than the drawing of a car, for example. And it's an astounding feat of structural biology. Because this has maybe, thousands and thousands of atoms. We can place every single atom in this antibody right where it is. So this is a real picture. And the cool thing is, once you can do that, you can say, you know what? How does an antibody bind and neutralize a virus? How does it do all of these different things? And this figure led to this very simple concept. An antibody has two arms and a stalk. I won't get into what this does, but it supports this. Each of these arms is identical, and guess what? Each of these arms can bind what we call the antigen. It could be a virus, it could be a cancer protein, and this is actually real. We know that this site here binds, that's how it works. This identical site here binds, that's how it works. Then you can cut it apart, you can say I want to work with this part, and you can start doing what we call not antibody production from natural sources, not antibody characterization, figuring out how it works, but the big field I became involved in, which really took off in the 90s and in the 2000s, was antibody engineering, shown here. So now if you can purify antibodies, you can get their detailed molecular structure, You can understand how natural antibodies work. What's exciting is, well, if you really know how it works, as Feynman said, you should be able to build it. Can we now start engineering antibodies, changing them, and eventually making them from scratch? So if you look at this and flip it around, what's interacting with this ball is a bunch of little balls here. And again, this is a representation of something real. What we understood is every antibody has maybe 20 or 30 positions that change, and that gives you a given antibody. And 20 positions might not sound like a lot, but there's 20 amino acids, so any of those 20 positions can be any of the 20 amino acids. And 20 to the 20th is actually 10 trillion trillion. So looks, well, you know, what can you do with 20 places and 20 building blocks, 20 amino acids? You can make 10 to the 26 different molecules. Huge. So this is what we now work with. We engineer each of these sites. And you also asked me, how do you know what to put there? Well, that's where the brains and experience comes in, and what differentiates one design from another. But the good thing is, because all proteins are encoded by DNA, and as I told you, we could sequence DNA and we could synthesize DNA. Now we can change any of these positions at will and change the antibody little by little. What another guy named George Smith realized is, and I'll show you on the next slide, if you want to make new proteins and you change them one position at a time, it's going to take you forever to figure out. It's trial and error, right? But what if you could make 10 billion different changes all at once, throw them in a test tube and say, you know what, tell me which of these work and which don't. So that's what happened with the Nobel Prize to George Smith. He said, instead of a mouse, let's take a bacteriophage. So this is a phage that infects bacteria. And we can engineer it. So it has this DNA which makes this antibody. This virus has this DNA that makes this antibody. This virus has this DNA that makes this antibody. I'm showing 5, but you would have 10 billion of these. And all of this can be in like less than a milliliter of solution. So suddenly you have 10 billion different antibodies. There's no mouse here. These have all been designed by us, so they're engineered. And the beautiful thing is, you just say, of these 10 billion, which 1 or 2 or half a dozen recognize my virus or my cancer protein? You literally throw them at it, and you literally wash the plate. This is all done on a plate. You say, here's 10 billion, throw them on this. The ones that stick we want, so we wash the plate. It's a virus, you can make more of those. Within a week, you can reduce 10 billion to half a dozen or so that have this very special property. They bind and neutralize the virus, or they bind and neutralize the cancer protein. And suddenly you have a drug. And that literally is what a drug does. A drug is something that interacts with a bad actor, be it a virus or an oncogenic viral cancer protein, and neutralizes it. And the amazing thing is this single library, we have one of these we made 15 years ago. We can still use it. So there's 10 billion in there. You know, for this target, these 5 work. The other ones are still there. You do it. So my group has taken this library, and we have others, but one does it. We've thrown it at close to 1,000 different targets, we call them, each one associated with some disease of interest. And we've developed more than 10,000 different antibodies against those targets. And each of those antibodies has the potential to be a drug. We've already moved a number into other companies or spun out companies. A number of them are now in clinical trials. So very rapidly you can develop drugs that are antibodies, but they're synthetic, because if you trace it back, we designed 10 billion, And then whatever comes out, it may have been 10 billion, but we designed every one of those. And some of our drugs are now in late stage clinical trials. So it becomes very powerful. And here's just a little figure of antibodies at work. So all of these you can then determine what we call the structure. So what you'll see here is these little gray things. All you need to know is they look different, right? So that's how proteins are. They have different shapes. So these are all different proteins bound to an antibody we developed. And in the antibody, what's different is that little face that binds there. And that's what I showed you. So even the antibody, its little surface, that mutated region, and this one binds this one binds this one binds this. And each of these is a disease-associated protein. So on this slide alone, we have, 45 potential drugs that we have the molecular structure of. And some of these, I can't tell you which ones because I don't even know the shapes, but you can trust me. And if you can do it that many times, why not do it hundreds of times? So that's what's freed us to go beyond natural antibodies. Now, anytime we know from research that, you know what, we think this protein is involved in inflammatory bowel disease, we can simply say, well, you know what, let's see if that's true. Let's make an antibody that targets that protein, maybe take a few months. Let's make large quantities of it. And we can then put that into, say, a mouse model and eventually humans. And you answer the question, did that protein cause the disease? Yes, it did, because when I develop an antibody that neutralizes it, the disease gets better. That's the best case. Or does it not? Even that's good knowledge. Oh, we were wrong. Let's move on to something else. And it does become that simple. You can say, this protein, I think, does this. Let's develop an antibody. Let's see if neutralizing it reverses the disease. And we've done that now a number of times. And if you can do it once, why not 10 times? Why not 100 times, right? So that's where we are. And later I can tell you about multivalence. I was doing a postdoc at Genentech, and in the 2 years I arrived, they'd approved Rituxan for lymphoma and Herceptin for breast cancer. I happened to be where the revolution happened. Why not join the revolution? No bigger thinking than that. If you're working at the most successful place and the biggest breakthrough in drugs in the last 5 years, you should probably start doing that. Well, my area of interest is to cure human disease in a new way. So if you're doing that, don't be so arrogant to think you shouldn't jump on the boat that's going in the right direction. Well, and that's, you asked me previously, how do people not be technicians? Ironically, don't think you're smarter than others. Work with people who are really smart, work with people who are really successful. You might end up being at least one of those, and hopefully both. When the first approvals happened around 2000 at Genentech and others, since then we've had hundreds approved for all kinds of diseases: cancer, virology, inflammation, etc. So yeah, that has happened. We're not the only group, luckily, doing it. And there's not a drug company in the world that doesn't have an antibody group. And there's hundreds of antibody companies alone. That's good news. This actually works. But what you'll notice here, or I can explain to you, and what's exciting is everything we're doing, I kept using the word block, neutralize, inhibit. So almost all the antibody drugs to date have done that. If you know that a protein is causing a disease, the easiest thing to do is develop a binder and say, good, now it stops it from working. It's not that hard to develop something that destroys something, so to speak. So what has excited us is, can you also make antibodies that turn on signaling? Much harder. You have to create something that builds even in normal life. I think that's understandable. If something's a problem, getting rid of it is often. But you know what? What if the problem is you don't have enough of something? Well, then you got to actually be much more subtle and bring things together. And that's one of the reasons we've started developing what we call multifunctional antibodies. If the problem is these two proteins on a cell aren't being brought together, which is a signal, and that's literally how signaling works. You bring these two proteins together, it tells the cell to grow bone. And if it doesn't happen, but that's, as you can think about it, I'm not preventing something, I'm building something. But a minimum you need there is the ability to have, I'll go back here, rather than this arm being identical, maybe you want this one to bind one thing, this one to bind something else, and not stop them from working, but bringing them together and start working. So we and other people realized if you can have 100 drugs, that's what we currently have, maybe 100 antibody drugs, each one binding one protein and stopping it from working. If these arms were different, even 100 times 100 is 10,000. So that's exciting because, rather than inhibiting 100 proteins, could you have thousands of things where they're designed to bring them together? With the crucial difference being, actually, I want to turn on signaling. If you have anemia because you're not making enough red blood cells, can I bring together receptors that tell you, hey, you need to make more red blood cells? Or growth factors that enhance muscle growth, bone growth. Neurodegeneration is what it is, degeneration of neurons. If neurons are decaying, can we stimulate them to regenerate? If it's neurodegeneration, why not neuroregeneration? And all those things require turning things on, not destroying them, but creating networks. So as even in politics we've learned, it's harder to bring things together than it is to blow them apart. But it is really, in a way, that simple. But what's exciting is we and a few others over the last 5 years have started doing that, going beyond inhibitors to what we call agonists or activators. And that's going to be exciting because we could start reversing degenerative diseases, which as we all get older become more and more prevalent. What I just showed there, you have a mouse, it produces cells that produce the antibody. So that was the key thing here. I don't know if that's what you wanted.
And can you go to the next slide?
Yeah.
Okay. You can sort of point to what you pointed at and lit up those two circles.
Yeah, I'm going to start there with this. So, binding site. And each binding site binds an antigen, a virus, another target. And this is identical to this. So, two sites binding. That's pretty much the message from this slide.
Okay, and then the next one.
Okay. Now if you take this and rotate it, sorry, let me see. Oh, and this, you can take this fragment and start engineering it. You take this, rotate it, that's what we're looking at. This is the binding site. Each circle is a different position that you can vary with the 20 amino acids. So, 20 sites, 20 amino acids, 10 trillion possible different antibodies. And you take this, put it on the virus, 1, 2, 3, 4, 5, 10 billion. This is all in a single milliliter solution. Take this, throw it on the target, this one binds, and you're left with this. It gives you from 10 billion to 1, the 1 does the activity you want, i.e. neutralizes the virus, inhibits a growth receptor, etc. And examples of antibodies. The gray things are different shapes because they are each different proteins. each of those proteins is associated with some disease. The antibodies are shown here in color, and at this surface is what we've engineered. So every time this region binds here because we engineered it, this region binds here because we engineered it. There's 45 here, we've made 10,000 of these. So we went from 10 billion to 10,000. Each of those 10,000 is a functional antibody. One of them blocks this, another one blocks this, another one blocks this. And of course that's very powerful, because each of those could be a potential drug if blocking this or blocking this treats a disease. You know, it works in a model. And antibodies can be used in any model: cells, animals, humans. So the same thing can be used in anything to figure out whether you have a drug on your hands or not. How do you make drugs? You can do it a lot of ways, but one of the major understandings about how cells work is there's an inside of a cell and there's an outside. I think that's obvious to people. But there's a membrane which separates the two. And what's quite frankly amazing about human and other multicellular cells is the membrane, which is infinitesimally small. It's just a border between outside and inside. Probably contains, I'd say, 20 to 30% of the action. It's the border. It's where things are registered. And outside, you know what it is? It's the serum, it's the blood, it's the digestive system. Inside is 80% of the proteins, which I told you are the molecules of life. But what happens inside the cell in multicellular organisms, which is what we are, is controlled by the membrane, which is the border. 20% of human proteins are in the membrane, i.e. signaling. Not doing stuff, but relaying a message. And given that it's such a small thing, that's amazing. And insulin is a good example. You know what insulin does? It signals, please take up glucose from the blood into the cell. Not do something, just open the border to glucose. Glucose goes in, cell has energy, and nobody goes into a diabetic coma or whatever. So what's interesting is that signaling was recognized, I'd say about 50 years ago, as how you influence human biology. Cancer is too much signaling for growth. Neurodegeneration is not enough signaling for growth. IBD, inflammatory bowel disease, is too much signaling for an immune response. So amazingly, you can control a lot of human biology, which means control a lot of the diseases by just saying, hey, traffic light, on, off, which is very important because you don't have to build a pathway. You just open the door or close the door. You're not saying, oh my God, how do I cure cancer? Answer is you just turn off this signal. How do I cure osteoporosis? You turn on this signal. So that's an important paradigm shift. You don't have to treat a disease from the ground up. You just make one molecule that opens a gate or closes it, and a lot of things happen. Because when I say signaling, one protein called, say, insulin, when it signals, can alter hundreds of proteins inside the cell. So that's called signal amplification. So if you can do one protein right, it it suddenly alters a huge number of proteins. And we've learned that. We've learned don't try to build the solution. Just be the traffic cop. Let these guys through, don't let those guys through. And antibodies can be built to stop signaling, which I described, and excitingly stimulate signaling. So one target can influence hundreds of targets in a human cell. But be careful what you wish for. Don't hit the wrong target, because signaling can also go, you know what, that was the wrong signal. But it's an important point that when thousands of proteins are involved, you identify the right protein, which is a signal transduction, transmitting a signal. It can alter hundreds of proteins in one event. So that's what we look for, these linchpins that are major regulators of messages. So, I'm not going to change the activity of 100 proteins, but if one messenger taps into that and says, evolution has built this system, red blood cells depend on 100 proteins being turned on and off. You find the one that is the message, which is called erythropoietin, and then everything happens. So that's what we do. We try to find the linchpins. Everything I said is not debatable. It's just everybody does it. The question is, how do you do it? Do you develop small molecules? Do you alter the DNA, which I think is dumb despite CRISPR? You might have heard of CRISPR and stuff. It's like, do you really want to change your DNA? Which is like, not me. So we do it at a different level, but I doubt anybody in science would dispute the signal and the message is where you hit things. So that's not disputed. What's disputed is how do you alter the signal? Because you're never going to understand why these 100 proteins regulate anemia or lack thereof. Why do these 100 proteins regulate whether a nerve cell grows or deteriorates? But the constructive arguments arise around what level do you hit it at? DNA, mRNA, which you've heard about. We prefer proteins because we believe that's where the action is. I'm biased on that, obviously. That's my way of looking at it. But signal transduction was a major advance in people understanding how cells work. So we work at the molecular level. Cellular level is pretty intense. Beyond cells, there's organisms, organs, tissues, cells, and molecules. And after that, you get into DNA and stuff, which is just the recording device. So we believe profoundly and with evidence that the molecular level is where it's at. And the evidence is this. Every drug except a handful, that's where it works. There's some drugs you don't know the mechanism, and there's other drugs people say, I'm going to edit your DNA so you don't gain weight. I'm like, no, I'm not going to edit. So the molecular level is, for me, transient enough, which means you don't change anything. If you don't need the drug, a few days later you don't have it. It's transient. But effective enough that you don't need to build, you don't need an organ transplant, you don't need cell therapy. So that's what I believe in. But I don't think anybody in our field, which is treating disease, disputes, signaling is what we're all influencing. That's a fundamental thing. I'd say 98% of people agree. The great hope for me for understanding human biology is you don't need to understand human biology. There may be 200, 300, thousands of different signals, and this one does this, red blood cells grow. This one does this, neurons grow. This one does this. So it's actually pretty interesting that pathways that have evolved before humans existed can be manipulated by humans. It's a huge gift. Like, thank you. I don't need to know how immune cells work. I just need to know these signals cause them to work. It could take another millennia to figure out how the immune system works, but that doesn't mean we can't have the immune system work for us. If you understand, I turn this light on and suddenly immune cells attack cancer. You know, that's pretty profound. You do one target, which is called PD-1, PD-L1, which won a Nobel Prize and cured Jimmy Carter's brain cancer. You do one thing and suddenly 100 things are engaged. You know, it's that big. So it's like, but you had to do the right one. If you do the wrong one, nothing happens or worse. I think the most powerful thing is early detection, but not the scare factor. You might get this, so get on this. You know what? I like to have a few beers. I might get liver cancer. I'm not going to stop having the beers. I'm happy to treat diseases that exist, and it becomes kind of mission creep. Why don't you just edit the DNA? Why should your kid have a propensity for disease? I'm like, you know what? Kids are all right, as the WHO said, they'll work it out. So I'm not a big proponent of preventive medicine. There, I've said it. If it prevents life, I don't want a medicine that says, you know what, if you sit in a room, you won't die of a car crash. Well, I might want to drive across the country. What do you want to do? So I think the best thing we can do with medicine is let people take more risks. You know, Neal, that's my point. Like, why do you build... I read this absurd report which says all alcohol is bad. Like, what are you talking about? You don't know what you're talking about. It's bad if you just isolate it and say, if you do this, it does that, but you don't want to stop people from living based on scientific data. I don't care. I actually don't care. If somebody wants to smoke a cigarette and his name is Keith Richards, I'm going to let him do it. If somebody wants to smoke a six-pack and he's in high school, I'll say, no, don't do that, but you don't want the Rolling Stones to say, well, you know what? Drinking and smoking is bad for your health. Well, it's good for society. That's my opinion on that. I mean, you can over-medicate everybody and everybody's safe and happy. Thanks. Safe and happy is not a lifestyle choice most people want. Insulin alone advanced, you know, the people who had it suddenly had 2-decade increases in life. And importantly, they had increases in lifestyle. Little kids who couldn't walk were suddenly going to school. That's important, right? Get kids who would not be able to function. I'd argue giving Elon Musk another 2 decades, not on my top list, but giving some kid who's 5 years old and he can go to school. So, you know, you have to look at these things. Who are you enabling to live longer?